Hello and welcome back to our next tutorial on electrical measurements and electronic instruments. In this video, we are going to learn about another type of instruments, ammeters, which we call moving iron instruments. These are very simple instruments. This is made up of mainly a coil, and this coil will have turns, okay, and this coil can carry some current. Let me call this current as I. So, this is the current, the unknown current that we want to measure. Now, we will have a piece of iron in front of this coil. Now, when any current flows through this coil, the coil acts like an electromagnet, like a solenoid, and therefore, it is magnetized and it will attract this iron bar, this piece of iron. Okay. So, the iron, this piece of iron will try to move closer to this electromagnet or solenoid. Now, what I will do? I will attach this iron bar to some pivot, and so that this iron bar can rotate around this pivot, and I will attach a spring. The spring will try to hold this piece of iron at its normal position. It will not allow the iron piece to move towards this electromagnet. And then what I will do? I will connect a long pointer to this iron piece, so that when any current flows through this coil, this iron bar will get attracted towards the electromagnet, and the spring will try to hold it back in its original position, but due to attraction, iron bar will move towards this magnet by some amount, which will cause this pointer to also move towards the left according to my diagram. And I can have a scale with markings like this, so that these markings will indicate the value of the current. The higher the value of this current is, this iron bar will be attracted more towards this magnet, this electromagnet, and this pointer will move more towards the left. Therefore, by observing the position of this pointer along this scale, we can measure the amount of current. So, according to my diagram, here I may have higher current values towards the left, maybe 10 ampere here, maybe somewhere here 5 ampere, maybe 0 ampere here, etc. Okay, or maybe 0 ampere here, depending on, or I may erase part of the scale. Okay. So, this way we can measure this unknown current by observing the position of this pointer along this scale. This instrument is called an attraction type moving iron instrument. Because this instrument acts based on the attraction between this iron bar and this electromagnet. We can have another type of moving iron instrument, which is more common in practice, and that is called a repulsion type instrument. So let us see how does that work. Once again, I will have a coil which will carry the current, unknown current. So let me draw the coil. And this is the conductor carrying the current. Let this current be I, the unknown current, and now I will have two pieces of iron bars instead of one. Okay. So let me draw them here. So this is one iron bar, and let this be another iron bar. Both are irons. Now suppose if I have current flowing in this direction, so it's like this, then it will generate flux maybe in this direction depending on the direction of the current. Okay. Therefore, both these pieces of irons will get magnetized, and maybe this side will be north and this side will be the south pole of this induced magnet. If this side is north for this induced magnet, this side should also be north and this side should also be south, because they are in same magnetic field, they are placed side by side, so they should have same polarity. If this side is north, then this side should also be north. If this is south, then this should also be south, or vice versa. So anyway, the like polarity, similar poles will be nearby. So this south pole and this south pole will repel each other. Similarly, these two north poles will repel each other. Now what I will do, among these two bars of iron, I will fix one of them to the frame of the instrument. So this is fixed, so this is not movable. And this one I can connect once again, say with a pivot. So then this iron bar can move up or down. I will connect a spring once again, so that the spring holds the this iron bar at some normal at a normal position when there is no current. But as soon as this current flows, this repulsion starts and the iron bar will move upwards. Okay. So now I can connect again a long pointer to this. And I can draw a scale here. So as current flows, the pointer moves upwards, and if the current is more, this repulsion force will be more, and the pointer will move further up and indicating higher value of current. So now I can possibly mark say this position by 0 ampere, this position by say maybe 1 ampere, this position by I do not know maybe some higher value maybe 3 ampere or so on. Okay. So we can mark these positions so that this pointer can indicate the value of the current. Okay. So this is called a repulsion type instrument. Now the next thing that we should do as usual is find out the expression of torque. Okay. So let's consider first this attraction type instrument. The idea that you should understand is that the force of attraction depends on two factors. It is proportional to two factors. First factor is how strong the the first factor is how strong this electromagnet is. So let me write strength of electromagnet this is one factor, and another factor is the strength of magnetization of this iron bar. So these are the two factors on which the force of attraction depends. Okay. So now this we can further write that this is proportional to, now the strength of electromagnet is proportional to the current I, because more the current is, we expect the strength of this electromagnet to be higher. So I am writing this as proportional to I. Now the strength of the iron bar or the magnetized iron bar or induced this induced magnetization will again depend on the strength of the solenoid or this electromagnet, which in turns depend on the strength of this current. So this second term also is proportional to the current, this current I. So therefore we can expect that the force is proportional to I square, and therefore of course the torque, which is nothing but force multiplied by some length, some distance, will again be proportional to I square. Okay. So this is one important result about the attraction type instrument. Now let us see what happens for a repulsion type instrument. So for a repulsion type instrument, once again the torque, okay, or the deflecting torque will be proportional to the force of repulsion, this force, and this will be proportional to once again two factors. And the two factors are the strength of this magnet and the strength of this upper magnet. So let me write it as the strength of say lower magnet according to my diagram. This is not a magnet, I mean this is the strength of magnetization, strength of better to write lower bar, I mean lower iron bar, this multiplied by the strength of magnetization of the upper bar. Now, this strength will depend on this current. More this current is, the flux lines will, the amount of flux density will be more. So, the magnetization will be more. So, this will therefore be proportional to I, and the second term once again is proportional to I. The strength of magnetization of each of this iron bar is proportional to the strength of this electromagnet or the current I. Okay. So, roughly, so therefore, once again the torque is proportional to I square. Okay. So, this is an important result about moving iron instruments, that the torque, deflecting torque is proportional to the square of the current. Now, let us consider the equilibrium condition. So, equilibrium by equilibrium we mean the situation when the deflecting torque is same as equal to the opposing torque given by the spring, so that at that position the two torques cancel each other and the pointer can stay at that position without moving further. So, at equilibrium we can write the deflecting torque is same as the controlling torque or opposing torque given by the spring. This is true for both type of instruments, no matter attraction type or repulsion type. So, controlling torque by spring, and this deflecting torque we know is proportional to I square. So, we can possibly write that this is equal to some constant k multiplied by I square. So, this is some constant okay, and the right side will be equal to let me call it k1, let me call it this k1 and k2. So, this is spring constant multiplied by the theta, the angle of deflection. So, this will imply theta is equal to k1 by k2 I square. So, this we can write as some constant k, k1 by k2 some constant times I square. So, we observe that the angle of deflection theta is proportional to I square. Therefore, on the scale if I have 0 ampere here and if I call this as my 0 degree position or 0 degree angle, then say for 1 ampere current I get 5 degree deflection. So somewhere here at 5 degree, okay, or maybe this is more than 5 degree. So I will have 1 ampere. But now 2 ampere current will cause the pointer to move by an amount 5 degree multiplied by 2 square equal to 20 degree. So it will be somewhere here maybe. So observe the scale is non-uniform, or we say non-linear. Okay. So because the angle of deflection is proportional to I square, it is not proportional to I. So this is one important property of moving iron instruments. Now another important fact, another important observation is that the direction of pointer movement that is theta, or the direction of the torque this does not depend on the direction of the current. Okay. So let us go back to our schematic diagram. Suppose if I reverse the direction of the current from like this. So if I even reverse the direction of the current, but if the magnitude of current remains same, then also this iron bar will get attracted, because a magnet can always attract a iron bar. A magnet never repels an iron bar. Okay. So the direction of the torque will always remain same, unchanged in this situation. Once again, here if I change the direction of the current, then maybe all these currents will also be reversed, and so therefore these flux lines will also be reversed, and this north and south will be altered. So this will become south and north, south and north, but still you see the similar poles are close by, so they are side by side. So once again this force will be still repulsive. We will never have attraction force between these two. So the direction of the current does not matter. The pointer will always move in the same direction. Okay. So therefore we can measure AC current with this instrument, okay, and the torque, deflecting torque Td will be, so as we have seen, is proportional to I square, Okay, so and if I is a function of time t, so we can write this is like this, and therefore the average torque, so time average will be time average of this I square t. Now what is this I square, the time average of I square t? This is nothing but, by definition, it is the square of RMS value of the current. So I RMS square. So average torque is proportional to I RMS square, and therefore the theta will also be proportional to I RMS square. Okay. So that's it in this video. In our next video, we will demonstrate you, we will show you a real instrument, a real moving iron instrument, and we will talk in more detail about subtle aspects of the construction and different things of a real instrument in our next video. Thank you.